Hi everybody, this is Miss Raina, your handy dandy neighborhood physics teacher, coming to you today from C347 at MacArthur High School in San Antonio, Texas, to talk about work, power, and energy. Look out for an upcoming quiz. First on work and power, then on energy, then you're going to have a test over both. What I want you to do right now is take out your guided notes paper, and we're going to start on the side that does not have a roller coaster on it. So find the heading called work, and under the letter A, you're going to write this definition right here. So what is work? It's the transfer of energy by a force. So that means you're going to need to remember everything that we learned about forces so that you can use that in case you need to calculate a force. Take this equation and write it in your equation box where it says work equals. All right, we have an important note here. Write this down at letter B. The force has to be in the same direction as the motion that's going on. So if I push something down, but it ends up moving sideways for some strange reason, then I can't calculate force based on those two vectors. Sorry, I can't calculate work. When I calculate work, I have to use a force and a displacement that are in the same direction. So you have room for an example here. Take this one. If I lift a kitten and I'm pulling the kitten up, 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 well, the kitten is having upward displacement because I'm applying upward force. Those are in the same direction, so it counts. Let's say I carry the kitten and I'm using force to hold the kitten up, but that force is applied in the upward direction, but I'm carrying the kitten sideways. So now the force and the displacement are in different directions. No work is done. So you guys go ahead and write that in letter C. And for the units used to measure work, we'll use a joule. That's the same as a unit for force times the unit for distance. So here we expanded it to kind of show you what a joule is. It's a kilogram meter squared per second squared. Okay, so then what's power? Well, it's the rate at which work is done. So write that down for the definition. When we say the word rate, we mean how quickly the work is done. So how do you calculate power? Write this down here in your equation box. Power equals the amount of work divided by the amount of time it takes. So the quicker you do your work, the more power you have. This you write down in letter C, the entire pink box. So if we know that work is force times distance, we can put this little portion in here in the power equation for work. And then our second option for calculating power, just write this bottom line as the second option in your equation box. You can do force times distance and divide that by time. So what units do we use to measure power? We're going to need to use watts. It's the same unit that you use in your house, like for a light bulb or like on your light bill. You can even use horsepower, and sometimes you'll see it that way when they try to sell you a car and they talk to you about the engine. So the word watt, that unit watt, was named after James Watt. He's the guy who invented the modern steam engine. So there you have E and F. And numerically, horsepower represents the amount of power that it takes for a horse to lift coal up from a mine. So what we used to do in coal mines is use an actual horse, and the horse would be pulling a line attached to a pulley, and every time we had to lift that heavy coal up and out of the mine, if a horse could lift 150 pounds 220 feet up in 60 seconds, that was considered 1 horsepower. The truth is that they bred small ponies to be able to do this underground, and so what you know as a horsepower is actually double pony power. Here's the conversion. Go ahead and fill in your blanks on letter H. 1 horsepower is 746 watts. We're going to go ahead and move on to some horsepower examples here. Here we have Lauren. She pulls sled across level snow with a force of 520 newtons. She pulls it horizontally and it moves 60 meters. Well, our formula tells us to get work, we got to do force times distance. When we multiply those, we get 31,200 joules. Think about this one. Here's the Hulk. He's carrying this weird bag of boulders. And so he's definitely applying upward force, but he's moving sideways. So how much work does he do? None. You guys take a minute and see if you can answer why for example 2. Alright, for example 3, Lauren does 31,200 joules worth of work in 27 seconds, and Alan does his work in 93 seconds. So the question is now, who is more powerful? Well, definitely it's Lauren. People tend to see this number right here, 93 seconds, and they think, okay, well, that's a big number, so he must be more powerful. But the opposite is true. Think in terms of how quickly somebody works. She did her work in 27 seconds. He took a lot longer. Because she worked quicker, it shows she had more power. All right, we're going to go on to the energy section and just remind ourselves, what is work again? Well, if we apply a force, then energy transfers if that force results in motion. How do we know that energy transfers? Well, we get movement. So kinetic energy, go ahead and write down that definition. It refers to the state of motion of object. Sitting in your desk at school, do you have kinetic energy? Well, no, you don't have any motion. It's debatable, right? But in the reference frame of the classroom, no, you don't have any motion. Go ahead and fill in the blanks for C. The faster the object moves, the greater its kinetic energy. Here we have an equation that popped up. Write that in your equation box for kinetic energy. It equals 1/2 mv squared. Alright, so the work kinetic energy theorem tells us that the work done on an object by a force, and it relates that to the corresponding change in kinetic energy. In other words, why are they related? Well, if we apply force to something and we're able to get it moving to change its velocity, that gives it kinetic energy. It also changes the kinetic energy. So you can write this down for letter A under work kinetic energy theorem. It takes energy to do work, right? Yeah, go ahead and write down yes for letter B. Does the work done equal the energy expended? Yes, go ahead and write down yes, because the energy can't appear from nowhere and it can't disappear into nowhere. Energy can't be created or destroyed. Because of conservation of energy, the work done equals the energy expended. You're going to write this down in your equation box or wherever you have room. Your equation box says work dash kinetic energy equals. Scratch out the equal sign. This is the equation, or this is the mathematical statement that I want you guys to write down. So this is now a second option for us to figure out how much work is done. We can do force times distance, and or we can figure out what our change in kinetic energy is. So if we want to know how much work is required to accelerate this car from 20 to 30 meters per second, we can use this theorem, figure out how much the kinetic energy changed, and we'll have a way to figure out our work even though they gave us no force and no distance. So I have a little bit of trouble figuring out how to write on this screen in the video. I would encourage you to try the examples for the work kinetic energy theorem. I have a feeling they're going to be pretty easy. If you have any trouble, come on over to class and ask me. Until then, see you next time. Have a great night, guys.